All right, I'm going to work through the practice final and try to explain a little bit about each of the questions as I go through. All right, so this will be the key. Mass is the measure of how much matter is in something. So if something has more matter, like a planet, then it'll have more mass than, say, like a computer mouse or something. Mass is measured in kilograms. So I said in class multiple times, like a desk is about 8 kilograms. I'm about 70 kilograms. Anyway, measured in kilograms goes with mass. For acceleration, that tells us how fast the velocity of something is changing, so the rate at which velocity changes. We talk about that. For free fall, if something's falling in the air, it's got an acceleration of 10 towards the ground. That means every second that it's in the air, it's going 10 meters per second more quickly towards the ground, or more slowly if it was moving upwards. So that's the rate at which our velocity changes. Power is the rate at which energy is added to the system. So it'd be E. I is the initial height of an object. So again, our Y direction is the up-down direction. Our X direction is the sideways direction. The normal force is the force, like if I press down on this table, the normal force is the thing that's counteracting my force. It keeps an object from falling through a surface. So if the table did not apply a force back on my hand would go through the table. You can try that with like a cardboard box. You can actually crush a box like that because it doesn't apply enough force. All right. Normal force. So that would be I. Work is the change in energy. So it's the way you change the energy of a system. Energy is measured in joules, which means that work will also be measured in joules. VIY is your initial velocity in the Y direction. So that would be Y is our vertical direction, so that'd be B. And then V cosine of theta, we do for angled launch problems, we draw theta here. This is our velocity. We break that velocity into two components, Vx and Vy. Okay. So that would be a horizontal component of velocity. So that's J. For K, that's our spring constant. So that would be G. And then delta X is it's the change of something, or it's like a displacement. That's another name for like the change in position. X is our position variable, so this would be the change in position. So C. Okay. Move on to this section. We did these at the beginning of the year. So it says Caroline starts at x equals 0. So she starts here. She walks forward 5 meters at 1 meter per second. 1 meter per second means that each second we move in this direction, we've got to move up by 1 meter. Okay, so that means at 1 second in the future, we will be 1 meter ahead of where she was originally. All right, 2 seconds in the future, she'll be 2 meters ahead of where she began. 3. Again, each second, we're just going 1 meter up. We'll do that for 5 seconds. Then she turns around and walks backwards at 2 meters per second for 3 seconds. That means that each second, she'll now cover 2 meters. So between seconds 5 and second 6, she's going to move 2 meters. She's going backwards, so we call that down in our graph here. So this is her moving backwards at 2 meters per second for 1 second, 2 seconds, and 3 seconds. Then she pauses for 5 seconds. So 1, 2, 3, 4, 5. And then walks forward at 0.25 meters per second. That means that each second, she's only moving 1/4 of a meter. So you can think 0.25, that's like a quarter. A quarter is 25 cents. So it takes 4 quarters to make $1. So after 4 seconds, she'll have made 1 full block or 1 full meter. And then she keeps going at 1/4 of a meter every second for 10 seconds. So she'll end up right there. And I'll use a ruler. This is a continuous graph. That means that you can look at any point on the graph. I could look at like the 2.5 second mark, and this graph would show me where she is. So it's important to draw the line between all of the dots. All right, so that's it for that problem. Now we got a couple questions about acceleration. The first one is Alexis hits a home run. As soon as the softball leaves her bat, which way is it accelerating? Okay. There's a couple things you could use to answer this. One is that we've talked about anything unsupported in the air is always accelerating towards the ground at 10 meters per second squared. So we would say that this is accelerating downwards. Another way you could approach it is by drawing the initial velocity and the final velocity and saying that acceleration is final velocity minus initial velocity over time. So I'm going to do the drawing on here just so you can see it. You could reason through this in your head, though, just saying, okay, every second the ball is in the air, it's going to be moving towards the ground faster. So right after it hits Alexis's bat, it's going to be going like this. Later on in time, it's going to be going, straight in the air, and then it's going to start to come down. Whichever arrow you draw for the second one, as long as it's something that happens later on, so as long as it's something that's less pointed up, you'll still get the same answer. So this is VI. This would be VF. We're trying to find the acceleration between these two vectors. So I do VF minus VI. So VF, right here, minus VI would be starting here, and I draw an arrow in the opposite direction as VI. So this is VI, okay? This resultant vector right here would be delta V. So VF minus VI. So that is the direction of our acceleration, because our acceleration A is equal to delta V over T. So our answer here is down. Again, VF minus VI, so our net vector, that's the same as just a downward pointing vector, be down. A plane flying south slows down. What direction is it accelerating? Okay, so I'll draw this with the arrows again. That's not a good south direction. Let's call south downwards. All right, so this is VI. So initially it's going at some large speed. At the end of the problem, it's going to be going at a smaller speed. So I'll draw VF. So it's slowed down. If I do VF minus VI, I do VF minus VI. So start at the end of this vector and draw my new vector, minus VI. So it's negative VI, just like this was negative VI. My resultant vector, so the vector that's the same as those two added together, is a vector that goes like this. So that would be delta V. Okay, so this is the direction of our acceleration. In my coordinate system, if down is south, that was the direction they were originally moving, upwards would be north. So I would say north for this. Yeah. So if you're accelerating north, you're slowing down if you were originally moving south. You could also be speeding up going north. But those are our two answers for that. Okay, we'll move on to our second page. These are all free response questions, so I'll just walk through what type of question each one is, and then go through solving it. Okay, it says, how long does it take Jack running at 5 meters per second to travel 1,500 meters? All right, the first things that I'm seeing when I see this are meters per second. That tells me this is velocity, and then meters, which tells me that this is a distance. So I could either say this is D, or I could say that's delta X. Those are measured in meters. Okay. It's asking me to find how long, so that's a question of time. So I'm looking for time. I know velocity, and I know delta X. All right, the equation that ties all of those together is this one right here. So V equals delta X over T. So I'll just write that down. So V equals delta X over T. I already get 1 point for the problem for writing that down. The next part is I just plug in my numbers, and then I can solve. You could also solve it algebraically by moving these things around if you're not comfortable doing it. Just plug in the numbers. So V is 5. That's equal to 1,500 over T. I'm trying to find T. So I'll multiply both sides by T here. These ones cross out. I get T times 5 equals 1,500. To get T by itself, I just divide both sides by 5. I get T is equal to 300 seconds. It's an S for seconds. Okay. All right. This next one, it's asking Sam accelerates onto a highway starting from 10 meters a second. He merges onto the highway after accelerating for 100 meters. Final speed on the car is 30 meters per second. What is his acceleration? Okay, so this is going to be another sort of velocity problem. I'm going to identify what I know first. So I know this is VI. This one's VF. This one here is how far they've gone. So that's our change in position or distance, whichever one you want to use. And then I'm looking for A. All right, so now I want to find a formula that involves delta X, VI, VF, and A. Right? In my problem-solving framework, I would do VI equals 10, VF equals 30, delta X equals 100, and I'm looking for A. My picture is, a car going onto the highway here. Okay. So now I look at my formulas. I try to find one with VI, VF, A, and delta X, and no other variables. All right. So I can look at these. That one's got T, don't want it. It's got T, don't want it. It's got T, I don't want it. So this one doesn't have a T. It has delta X, A, VI, and VF. So I'll use that formula. So VF squared is equal to VI squared plus 2A delta X. All right. Now I'll go through and solve. So I'll plug in my numbers. So VF 30 squared is equal to 10 squared plus 2. Again, A is what I'm solving for, so I'll leave that as a letter. A, and then delta X is 100. Okay. So I get 900 is equal to 100 plus 200A. It's just a simplification step. Move my non-variable term over to the other side, so I get 800 is equal to 200A. By 200, I get 4 is equal to A. Right. My units for this are going to be meters per second squared. All of my answers should have units. Okay, so my answer should be 4 meters per second squared. Yeah. Okay. Our next one, Fabian throws a pencil horizontally off the top of the gym from an initial height of 7 meters and with a speed of 16 meters per second. How far away does it hit the ground? So this is a horizontal launch problem. We'll have to use a calculator for this one. Let me get a working calculator. The way we do a horizontal launch problem is we split it into 2 parts. One's a vertical component, one's a horizontal component. Those are independent of each other, but they're tied together by the time it takes for the thing to drop to the ground. Okay, we did a little experiment with the expo marker and the blowgun to show that whether something is moving horizontally and falling, like so whether it's a horizontal launch or whether something's just dropped in the air, they're both going to take the same amount of time to get to the ground. What that means is we can treat it as one problem where you're just doing a free fall problem where something's falling from a height to the ground, and then a second problem where something's moving at a constant speed sideways for a given amount of time. It looks like for this one, I'm looking for how far away does it hit the ground. I'm given its initial height and its initial speed. So given its initial height, I can figure out how long it's going to take something to fall to the ground. So if something's 7 meters above the ground, I can figure out how many seconds will it be between when it's dropped and when it hits the ground. Once I know that number of seconds, I can multiply that by my speed, and I can get how far away it hits the ground. I'll use the problem-solving framework just to keep myself organized here. So I know height. So that would be y initial is equal to 7 meters. All right, I'll draw my picture here. So this is like 7 meters. It's being thrown. It's going to hit the ground somewhere like that. Okay. My initial speed is 16 meters per second. If I call my initial height, or my initial y position 7 meters, then my final y position will be 0 meters. So it started at 7, ends at 0. I'm also going to call, I don't really care about xi, but if I wanted to, I could say xi is equal to 0. Other things I know, the acceleration of anything in the air that's unsupported is 10 towards the ground. I'm going to call that negative 10. So A is equal to negative 10, and it'd be meters per second squared. We are looking for delta x. We're looking for how far away it lands, its change in horizontal position. We're going to need to find time first. This is its acceleration in the y direction too, so AY. All right. So the first thing I want to do is find time. I know YI, YF, and AY. I know that the y direction tells me how long it's going to take to hit the ground. If it was from a higher height, it would take longer to hit the ground. So that's the thing that's determining how much time this thing is in the air. For an equation, I need something that involves y final, y initial, acceleration, and time. So I'll look at my equations. Remember that each one of these where it's got an x, you can also replace it with a y. It's just, these are general equations for position coordinates. They can be either y coordinates or x coordinates or z coordinates, whatever coordinate system you're working. So I'm looking for one with initial position, final position, acceleration, and time. If I look at my first one, got initial position, final position, acceleration, time, and then I've also got VI. Do I know VIY? All right, so if it's launched horizontally, that means that it's not moving up and down in the y direction. That means that VIY will be 0. Okay, so I do know VIY, so I can use this first equation here. I'll plug in my numbers, and I get y final is 0. That's equal to the initial y, so that would be 7, plus VIY is 0 times t, plus 1/2 times 10, negative 10, times t squared. I'm trying to solve for t. I should really write my equation out in terms of letters here. Y final is equal to y initial plus VIYT plus 1/2 a t squared. Okay, that's my equation that I'm using. There's me plugging in numbers. I'll simplify this. 0 equals 7 plus negative 5t squared. Trying to get t by itself. I'll move 7 to the other side by subtracting 7. So I get 7. So you go to negative 5t squared. Divide by negative 5. I get 1.4. So you go to t squared. Plug it into my calculator. Square root of 1.4. 1.18 is equal to t. 1.18 seconds is equal to t. All right. I know my time now. Oh, shoot. Can we see that? All right. So I messed that up. The things that I've added, I've changed VIY. I said that equals 0. That's another piece of information that I knew. And then I walked through which equation I was going to use. So I wrote down my equation, I plugged in my numbers, and then I simplified it down to where I found out t. Again, I chose that equation because it just involved things that were in this column, and it let me figure out how much time it's going to take before it hits the ground. So now that I know how much time it takes before it hits the ground, I will use that to figure out how much distance it went. So if it's in the air for 1.18 seconds, and it's moving at a speed of 16 meters per second, so that would be Vx is 16 meters per second. Again, the x here is just saying like in the sideways direction. I can figure out how far it goes because I've got this equation where v is equal to delta x over t. So my velocity tells me how far something moves in a given time. My velocity is 16. That is equal to delta x, that's what I'm looking for, divided by 1.18. That's the time that I just found. All right. To get delta x by itself, I'll just multiply both sides by 1.18. 1.18, and I get 16 gets me 18.9. So delta x is equal to 18.9. My units are meters because it's distance or displacement. Okay. That's it for that page. All right. So for this problem, Michaela is sitting in a shopping cart wearing a helmet. Her friends have taken her to the top of a 20-meter tall hill. Her plan is to ride down and hopefully not crash. Assume that Michaela and the shopping cart have a combined mass of 60 kilograms. How fast will she be moving when she reaches the bottom of the hill? Okay. When I see this problem, I think of, oh, this is similar to a roller coaster. So I've got a hill. I've got something starting up at the top of the hill. It's going to end up going fast at the bottom. The method I'm going to use is conservation of energy for this. That'll be the easiest way to solve it, and the only way that we can solve it given the numbers or the information that we've been given. I'm going to use the problem-solving framework just to, again, keep things organized. So I know 20-meter tall hill. That's the height that I have at the beginning. All right, height equals 20. Plan is to ride down, hopefully not crash. Assume that Michaela and the shopping cart have a combined mass of 60 kilograms. So M equals 60. Okay, I know that g is always going to equal 10 meters per second squared. Doesn't matter if it's positive or negative. For energy, we generally use positive. If you use negative, you'll end up with a negative sign. You just gotta not get too worried about that. We're looking for her velocity at the end. All right, so we can draw our picture here. So shopping cart. And we got Michaela's head there with the helmet on. Good. Going down the hill. Okay. So what I'll use is conservation of energy. My equation for that says that the energy of my system at the beginning of the problem is equal to my energy of the system at the end of the problem. Okay. At the beginning, I'm thinking I've got something at a high height, so I'd say that that is our gravitational potential energy. Again, there's only 3 types of energy that we've used in calculations. We got gravitational potential, we got kinetic, and we got spring. Gravitational potential has to do with how high something is. Kinetic energy has to go with how fast something's moving. So at the beginning of the problem, I've got my gravitational potential energy. At the end of the problem, that's all going to be turned into kinetic energy. So all the energy that the cart had from being at the top of the hill will go into it going really fast. So this will go EK. All right. So now I'll just plug in my formulas for these. So I know that EG is the same as mgh. I know that EK is the same as 1/2 mv squared. Okay, looking for V. I know M, I know G, I know H, I know M. So I should be set. So I'll do 60 times V. One thing you could do, if you wanted, you can divide both sides by M. If you want to plug in numbers, you're welcome to do that as well. So M times G times H is 20 is equal to 1/2 times 60 times V squared. Looking for V squared. I'll simplify this. 60 times 10 times 20 would be, I think, 12,000. That'll equal 1/2 of 60 is 30. V squared divided by 30. Okay, and I should get, it would be 4 followed by 2 zeros, so 400 is equal to V squared. That tells me that V is going to equal 20. I just take the square root of both sides. My velocity is always going to be 20 meters per second. So the unit for velocity is meters per second. So 20 meters per second is equal to V. Again, remember to put your units. Okay, next problem. How fast will a 0.15 kilogram baseball accelerate if Cassidy pulls it 2 meters back in a 110 newtons per meter slingshot? And let's go. Okay, this is talking about an acceleration. We didn't talk about accelerations in the unit for energy. That means that this is coming from a different unit. The thing that I know that connects to acceleration is a force. So there's a connection between forces and accelerations. Forces cause accelerations. What that means is if I can figure out what force is acting on this baseball, then I can figure out how quickly it will be accelerating. So my formula for that, ultimately, that I'll use is F equals ma. Let me just draw out my picture again with what I know, what I don't know, what I'm looking for. Okay, so we got a mass is equal to 0.15. We got K, that's our spring constant, 110. And we've got pulls it back. So the amount that a spring is stretched, our variable for that is delta x. It's equal to 2 meters. Okay. We are looking for acceleration, so that's A. To find acceleration, I'm first going to have to find force, because a force is something that causes an acceleration. I can get the force using the spring force from this. So I'll find F, then I'll find A. My picture for it would be just like a slingshot here. And there's a baseball there, and it's been stretched 2 meters. Okay. So ultimately, I'm going to get F equals ma. That's the thing that connects acceleration to force. For the force, I'm going to use the spring force. That's the thing that's involved whenever you stretch a spring. So I'm going to say the spring force, that's my total force, is equal to ma. All right. Now my spring force is given by K delta x. So I will put the negative sign there. The negative sign doesn't matter too much. So negative K delta x is equal to ma. Again, that just comes with the formula. You could ignore that. All right, now I've got F taken care of. I've found F. Now I just got to find A. So let me plug in my numbers and then solve for A. So K would be 110 times delta X. You only have to worry about this negative sign if you're adding multiple forces together. Since we've only got one, it's just telling us the direction of the force. We don't have to worry about it. Delta X is 2. That is equal to mass is 0.15 times A. So 220 is equal to 0.15 A. Divide by 0.15. Do 220 divided by 0.15. I get 1,466 meters per second squared. That's our acceleration. I guess technically it should be 1,467. I don't care too much about the rounding. If you're close, I'll give the points to you. In physics, we're just trying to get close to a right answer. Okay. There's that problem. Our next problem. Noah is going to pull Michael into town Napoleon Dynamite style. Michael has a mass of 70 kilograms and coefficient of friction of mu equals 0.08 with the ground. How much force is required to pull him with a constant speed? All right. Key here. It says constant speed. That tells me something. That tells me that the speed is not changing, which means that my acceleration is going to be 0. So if I'm pulling something at a constant speed, acceleration will be 0. Okay. I'll do the same setup here. So let me write down the things that I know. I know mass is 70. I know that mu is 0.08. Okay. And that's all the numbers that they give us. I know that g is always going to be 10. Okay. It asks us, what is its acceleration? I'll keep these hints on the file itself. What is its acceleration? Well, we can start off, we could say A is equal to 0 because it's got a constant speed. Okay. We also know F equals ma. The sum of the forces is equal to ma. So if we add up all of our forces, we're going to get m times a, which is equal to 70 times 0, which is equal to 0. This means the sum of the forces is equal to 0. Okay. I forgot to write down what we're looking for. We're looking for the force that they're pulling with. I'll just say force pulling there. This little P there. In our picture, we got one person on a bike. That's a bad bike. All right, so somebody on a bike, and they are pulling somebody that is on rollerblades. At a constant speed. Okay. Sum of our forces is 0. In this diagram, I can label the forces that are on Michael. So there's two forces acting in this direction, and then there's one going up, one going down. So I know that gravity is always pulling Michael down. I'll just do this in terms of a free body diagram. So I've got the force of gravity pulling him down. He's not accelerating upwards or downwards. That means that the normal force must equal gravity. So I'd say that's the normal force. Then I've got the force that we're pulling with. You could label this tension if you wanted. I'll just say FP. And then in this direction, we've got friction. All right, all of these add up to 0. The first thing that I'll do is figure out, all right, so I've found what is the acceleration. I found the sum of the forces. Let me find the force of gravity. So force of gravity is equal to mg. That's my formula for it. So that'll be 70 times 10, which is equal to 700 newtons. Okay. Force of gravity is exactly canceled out by the normal force. That means that the normal force is also equal to 700 newtons. Okay. We know that force of friction is equal to the pulling force, again, because those exactly cancel each other out. So I'll just say force of friction is equal to the force that's pulling. And again, this is from sum of the forces equals 0. So they've exactly canceled each other out. So now for the force of friction, I know that it is mu times N. So that'll equal Fp. So I've just replaced force of friction with what it equals, and then I can plug in my numbers for mu and N. So 0.08 times the normal force, which is 700. That'll give me Fp. I get Fp is equal to 0.08 times 700. 56 newtons. All right, here's my answer. Okay, last page. A 1,200 kilogram car moves at 9 meters per second. How much force would be needed to stop it over a distance of 5 meters? How much force would be needed to stop it over a distance of 2 meters? So this is saying, like, if you got a car, if it stops over a long distance, it doesn't have to use as much force as if it stops over a short distance. I'm trying to think of some analogies to this. So, like, if you're landing on the ground, we kind of did this problem, but if you bend your knees, you're stopping yourself over a longer distance. That means that your joints and stuff are going to experience less force than if you stop yourself over a short distance by just hitting the ground and not bending your knees at all. The formulas that go along with this, at the beginning, the car has some amount of energy. For it to come to a stop, all of that energy has to go away. The way we change the energy of a system is by doing work, so that's F times delta X. I'm just going to write down what we know first. I won't use that framework because it'll be hard because we got parts A and B. Anyway, my initial energy that I have is kinetic energy because I've got this car that weighs this much and it's moving this fast. So since I've got a velocity, I know that it's kinetic energy. Okay, so and kinetic energy is 1/2 mv squared. That's the same as 1/2 times my mass is 1,200. V is 9. That would be squared. So 0.5 times 1,200 times 9 squared. Okay, and I get 48,000. My unit of energy is joules. So that's its initial energy. At the end of the problem, it's not moving at all. So we'd say our final energy is 0. Okay. I can use these two to figure out the change in my energy. And by doing that, I can figure out how much work has been done. So delta E is equal to E final minus E initial.